Hey AP, in this video, we're going to talk about rate laws. So in our last video, we talked about different ways that we can speed up or slow down a reaction happening. And this time we're going to look at, well, how can we quantify that into a rate? So how can we measure that? And we can measure it using a couple of different methods. But first we should start at the beginning. So a mechanism, which we've talked about briefly, is an elementary step that makes up the complex chemical reaction. And we looked at those with potential energy diagrams. And we said that each elementary step has a potential energy diagram associated with it. And we can look at our reactants, our transition, our activated complex in our transition state, and then we can get to our products. And we have talked about that the rate is going to be dependent upon the slowest step. And we call that the rate determining step, or RDS, which is the slowest elementary step of all of them given to us. And sometimes these are given to us in terms of a mechanism. Other times it's going to be experimentally determined. But regardless, we're going to have a rate given to us. And we have this rate equation, otherwise known as a rate law, where we say that the rate is equal to some rate constant K times, these brackets say concentration, so times the concentration of the different compounds in our reaction. And these are our reactants. And then their order, because every reactant has a different order of rate associated with it, depending upon how much changing this reactant speeds up or slows down our reaction. We get different orders. So we have our concentration of our reactant raised to an order. And depending upon how many reactants we have, we'll have more or less listed in our rate law. The overall order is the sum of the individual orders. So that means that if this was a 1, a 2, and a 3, my overall order would be 1 plus 2 plus 3, which would be 6. Okay. Go ahead, pause for a second and copy down these 8 notes about rate laws, and then I'll walk through them in a minute. All right, so notes about rate laws. First, the order has to be determined experimentally. Unless we're given our mechanism, we can't figure out, which we usually don't know, we can't figure out the order just by looking at our reaction. We have to get experimental data. The units and the magnitude of the rate constant are super important, and those get determined through calculations and looking at units on our calculations to determine the units of the rate constant. Okay, and you'll be asked to do that. So super important, this unit, that we leave units on our numbers. Third, the reactant with no effect on an order or on a reaction has an order equal to 0. So that means that if I were to change the concentration of A and my rate stays the same, that means that the order of K in my reaction is 0. So it just doesn't have any effect. 4, the orders can be fractions. Although we like to avoid fractions if we can have an order of a half. It's very rare, though, in our circumstances. The sum of the elementary steps has to add up to the overall complex reaction, which is what we just talked about here. Then intermediates are formed in one elementary step, and then they get used up in the subsequent step. And we'll take a look at that, what that means down here. But intermediate is a new term for us. If a substance is present at the beginning and the end of the reaction, I didn't finish the words. It can be, is present beginning and end, it can be a catalyst. So a catalyst is present at the beginning, and it also comes out in our products at the very end, which means that it doesn't get used up. We still have it when we end our reaction. Then 8, a second order reaction rate equation says that rate is equal to K times my 2 reactants, A and B. Well, if my concentration of A is extremely larger than B, then we're going to say that, well, because A is in so much excess in a reaction, we're just going to say it's considered constant. And this will come up a few times, and it'll tell you that in the problem. So let's start putting some of these 8 notes about rate laws into practice. First, it asks us to identify the catalyst and the intermediates in the following mechanism. So we can see we have a 2-step mechanism. I have sulfur dioxide plus this vanadium oxide complex, make sulfur trioxide and a different vanadium oxide complex. And then that vanadium oxide, the V2O4, reacts with oxygen to make V2O5. So we had to identify a catalyst and intermediates. We said a catalyst is a substance present at the beginning and end of a reaction. So I look to see, do I have any compounds that are present in my original reactants and products? And I do. I have V2O5 is present at the beginning and at the end. So my catalyst is V2O5. An intermediate gets made in one elementary step and then used up in the next. So I look at my first reaction, I make SO3 and V2O4. I look to see, do either one of those get used up in my second reaction, or are they reactants? And I do. I have V2O4 gets made and then used right away. So that's an intermediate. V2O4. Okay. Well, what if I'm given a balanced chemical reaction? Could I write my rate reaction? And the answer is yes, we can get rates, but we're not going to get rate constants necessarily out of it. So if I have the following reaction of A plus B makes C plus D, the rate of reaction means that A is getting consumed in terms of its molar coefficient, right? This molar ratio. We have 1 over our molar ratio, so 1 over A, times, and this is a concentration, so you just have brackets around them, the change in concentration of A per change in time, okay, which is equal to decreasing, right, because they're getting used up, so negative 1 over B, my molar coefficient, times the change in concentration of B over the change in time. And then C and D are both being made. So these are positive, right? Because I'm making them. So if I'm making them, it's 1 over little c, my molar coefficient, times the change in concentration of C over change in time. And then same thing for D. Okay. This part here, if you're in calculus, you'll notice that it looks kind of like a derivative a little bit, but this is the rate. So this part here, the change in D over change in T, this is the rate of production of D. This is the rate of production of C. This is the rate of consumption of A, the rate of consumption of B. Okay. So let's put this into practice. For the following reaction of 2NO2 to 2NO plus O2, write the rate law in terms of the reactants and the rate laws in terms of the products. So in terms of our reactants, we are going to say that the rate is equal to my reactants that I have here. So negative, because I'm consuming it, 1 over 2 times my change in the concentration of my reactant, NO2, over the change in time. So that's in terms of the reactant. In terms of my products, I will have my rate is equal to, for my first product here, my nitrogen monoxide, I'm making this, so it's positive. So 1/2 positive, change in the concentration of NO per change in time. And I also have the rate of my other product, my oxygen. That is also positive, say 1 over 1, or just leave it as 1. Change in my rate of O2 over change in time. So if I were looking at my two rates of product production, I would notice that my rate of NO production is twice my rate of oxygen production. Okay, and we can see that because if my rate for these to be equal, right, because we can also say that my rate of products, 1/2 NO, change in time, is also equal to change in O2 per change in time. right? Well, for these to be equal, that means that this number must be twice as big as this one. That way, if we multiply by half, it's the same. So for example, to make these equal, 0.5 times the rate of 4 is equal to 2. That means that my rate of NO production is twice that of my oxygen production. All right. Let's do another example with some more numbers in it and less theoretical. All right. For a reaction, N2,3H2 makes ammonia 2NH3. Calculate the rate of disappearance of hydrogen when ammonia is made at a rate of 5.7 times 10 to negative 3. This is molarity per second. Remember, capital M in chemistry is molarity per second. All right. Well, first let's write our rates. So we know that we are going to have, based off of our balanced chemical reaction in terms of H2 and NH3, we've got H2 and NH3. So I know that my rate of H2 disappearing is negative 1/3 change in the concentration of H2 over a change in time is equal to my production, so positive change in the concentration of NH3 per change in time. Okay. We said this, different color, this here is our rate of production. So if we're told that NH3 is made at a rate of 5.7 times 10 to the negative 3, that this number is my rate. So that goes here. Okay. I'm looking for the rate of disappearance. That is this, my rate of disappearance. Okay, and this is the rate of it decreasing. This is the rate of it being made. So I'm going to plug in my numbers, negative 1/3, and I'm just going to call this whole big thing X because we're looking for this rate. This is a number. Equal to 1/2 times 5.7 times 10 to negative 3 molarity per second. When I get my calculations, I get X is equal to negative 8.6 times 10 to negative 3 molarity per second. Okay. Or we can say that H2 is consumed at a rate of 8.6 times 10 to negative 3 molarity per second. But you might ask, like, well, why do we suddenly turn that into a positive? Okay, well, this negative here, this tells us our direction. Okay. So it tells us that, hey, this concentration is going down by 8.6 times 10 to the negative 3 molarity per second. It's not increasing. But I can say in a positive fashion, hey, I'm consuming it this fast. That's how fast I'm consuming it. Okay, so just take note about directionality of your rates so that way you don't get something mixed up when you are plugging in numbers. Okay, so that's how we can calculate rate based off of a balanced chemical reaction. Well, what if we're just given a mechanism? How can we then figure out rate from a mechanism? Well, we have to look at our rate determining step or our slow step. So remember that rate is equal to K times the concentration of my reactants raised to their order. Okay. And that is based off of my slow step. In the slow step or the rate determining step. Okay, we can only write this out if we can figure out the rate determining step. So if we look at our chemical reaction, A plus B makes C plus D, our mechanism is listed below. I need to determine my rate law. So I'm just writing out what my rate law is going to be. Well, I have to look at my slow step. That's my rate determining step. And it says, well, hey, step 2 is your slow step. Okay. Well, I know that my formula is going to be rate equals my reactants in my rate determining step raised to their coefficients. So Q times B, and both of them have a coefficient of 1. So this is a 1 and a 1, but we don't ever write ones in chemistry, so that can just pretend it's not there, right? Go away. The problem with using this rate determining step is that Q is made and consumed. So it's an intermediate. So Q is an intermediate. That means that I never know the concentration of Q in my chemical reactions because I can't ever collect it. As soon as it gets made, it gets used up right away. So that means that I can't put Q inside of my rate law. Okay. So if I go back up here, I see that, well, Q is actually proportional to A. Okay. Q is made from A. So I can substitute my reactants of A in for Q. So now I can say, well, actually, because Q came from A, well, A is really just like Q. Or if this was A plus B, I'd have A and then B on here. Okay. And then B is still fine times B. And don't forget, I forgot our K, the K in there. Okay. So now this just so happens that it matches up for a chemical reaction. That's not always the case. This one just worked out that way. So what I can also say after I've determined the rate law is I can say the order with respect to each of our individual compounds or reactants that we have inside of our reaction. So you'll see WRT written on papers and in directions, and that just means with respect to. So my order with respect to A, my reactant A, is going to be 1 because the number written up here is 1. We just don't write it. My order with respect to B is also 1 because that's my order listed there, which means that my overall order of reaction, remember we just add up our exponents here, 1 plus 1 is 2. So my overall order of my reaction here is 2. So we now know, given a reaction, balanced chemical reaction, and we know about rate of appearance or disappearance of things, we can calculate rates. If we have our mechanism, we can calculate rates. But the stuff that we're going to see usually is experimental data. Okay, and there's 2 different ways that we can look at experimental data. Sometimes experimental data is given to us in a descriptive form, like this one. So many times we do not know the mechanism for a reaction, but we can manipulate concentrations of reactions and measure rates of product production. Okay, so we can measure rates. And we'll do this in a lab next week sometime. Yeah, I think next week sometime. So for the chemical reaction of BrO3 minus plus 5Br plus hydrogen ions, this is a redox reaction, right? For this reaction, determine the rate law. Well, our experimental data tells us that when we double our bromate, the rate also doubles. So that means that with respect to bromate, my rate, because my bromate doubles and my rate doubles, they move at the same rate, or they increase at the same rate. That means that my rate is proportional, and that's what the little fish means, the alpha sign here, is proportional to BrO3. Okay, they are the same. When one doubles, the other one doubles. If one triples, the other one triples. So that means that if they move in the same fashion, they are first order. Okay. So then similarly here, double Br doubles the rate. So again, with respect to Br, the rate is proportional. So if bromide ions double, so does the rate. So again, that's first order. But now let's look at this one. When I double my hydrogen, I quadruple the rate. So that means that if I double my rate, if I change my rate from, let's say we go from 1 to 2, my hydrogen, I doubled my hydrogen. Well, that means that my rate, if it started the same at 1, well, it was quadrupled, which is 4. It means it was 4 times the size. So this means a change from 2 to 4 is a squaring. So that means that my rate is proportional to my hydrogen ions squared. Okay, the rate of them is squared. So this is a second order reaction. Okay, so our rate law, we can see that it is first order in terms of Br, first order in terms of Br minus, and second order in terms of hydrogen plus. So that means writing our reaction, we would know that our rate is equal to K times our BrO3 minus to the first, our Br minus to the first, and our hydrogen ions to the second. And that would end up being our rate law. Ooh, I guess I missed this. Sorry. Like that. Okay. Now, most of the time, you're not given this in written words. You're given this in experimental data. So let's take a look what that would look like. All right, so numerical data shown for the synthesis of nitrogen dioxide from nitrogen monoxide in oxygen gas, shown below. So we've got our reaction here. We have 4 different experiments. We are told our initial concentration of nitrogen monoxide, our initial concentration of oxygen, and then we were able to measure the rate of formation of our nitrogen dioxide through some sort of means. Okay. If I'm looking at a reaction and I want to know, well, what is my reaction order with respect to nitrogen monoxide? Well, if I'm looking at what happens when I change nitrogen monoxide, that means that I must look at experiments where the other thing is held constant, so where my oxygen is held constant. Okay, so I see oxygen being held constant here. It's 0.15 and 0.15. So I'm going to look at experiments 1 and 2 for this one. You could also look at experiments 3 and 4, and you're going to get the same answer because in 3 and 4, this guy's also held constant. Okay, so I'm going to look at experiments 1 and 2. And remember that we can say that our rate is equal to K times our concentration of one reactant raised to its order times the concentration of our other reactant raised to its order. Okay. We know rates and we know concentrations, and I want to know, well, when I doubled my nitrogen monoxide, how does that impact my rate? Okay. Does it double? Does it triple? Does it quadruple? And that's going to help me figure out my order. So I'm going to look at the rate of, and I'm going to do, because my rate of experiment 2 is bigger than 1, I'm going to do experiment 2 on top, and I'm going to do experiment 1 on the bottom. So I'm going to say the rate of experiment 2, which is equal to 0.0192, is equal to K, which we don't know our rate constant, times the concentration of nitrogen monoxide, which we know for experiment 2 is 0.03, to the X, and oxygen, 0.015, to the Y. And that is over, so I want to know its relationship to one another. That is over the rate of experiment 1, EXP. Experiment 1. Experiment 1 has a rate of 0.048. K, my rate constant, times nitrogen monoxide, 0.015, to the X, and 0.015 to the Y, because that's my oxygen. Now, if we take a look, we can see that there are lots of things that are the same on the top and the bottom, so they can cancel out. For example, K is a constant. That cancels out. My oxygen concentration is also constant, so that cancels out. So what I'm left with is 0.192 over 0.048 equals 0.030 to the X over 0.015 to the X. Now, when we have two numbers on the top and bottom of a fraction, both raised to the same exponent, we can write that as 0.030 over 0.015 raised to the X, right? I can do that. That's a math thing. Okay. So 0.0192 divided by 0.048 is 4 equals 0.013 over 0.015. That's 2 to the X. Well, how does 2 turn into 4? Well, X must equal 2, which means it's squared. So that means that with respect to nitrogen monoxide, this is second order. So that means this guy is a 2. Okay. Now I need to figure out, well, what's Y? Okay. So what's my reaction order with respect to oxygen? Well, again, if I'm looking at oxygen, that means that my concentration of nitrogen monoxide must be constant. So what experiments does nitrogen monoxide have a constant concentration? I can see it's 0.15 in experiment 1. It's also 0.15 in experiment 3. So I'm going to look at experiment 1 and 3. You could also look at experiments 2 and 4 because nitrogen monoxide is constant there, and you would get the same answer. Okay. Again, I look to see which of my rates is bigger, and rate for reaction 3 is bigger, so I'm going to put that one on top so I don't have to deal with fractions. I get whole numbers. So got rate of experiment 3, which is 0.096, is equal to K times my concentration of nitrogen monoxide, which is 0.015. And we can write X, or we can put in the 2. I'm just going to write X and pretend I don't know it yet. And my oxygen is 0.030, and that's to the Y, divided by my other experiment, so the rate of experiment 1, which is 0.048, K, and this one stays the same, X, and then oxygen in this one is 0.015 to the Y. Again, like things cancel out, so the K's cancel out, my nitrogen monoxide cancels out, so I am left with 0.096 over 0.048, and then because these are both raised to the same exponent, I have 0.030 over 0.015 raised to the Y. So 0.096 divided by 0.048, 96 divided by 48 is 2. So I have 2 equals, and then 30 divided by 15 is 2 to the Y. That means Y must be 1, because 2 to the first is 2. So that means that this is first order. So Y is 1. So what's my reaction order of the overall reaction? Well, we have second order for the first one plus first order for the second one means overall my reaction is third order. I can write my full rate law expression now that I know my orders for both my reactants. So I say that the rate is equal to K, because I still don't know what K is yet, times the concentration of nitrogen monoxide to the second times the concentration of oxygen to the first. Okay. Now, because we know experimental data, we can plug in for my rate and my two concentrations to solve for K, which is my rate constant. So I'm just going to pick reaction 1 because that's easiest. So in reaction 1, I'm going to plug in for my rate, 0.048 is equal to K, which is what we're solving for, times my concentration of N, which is 0.015, and that's squared, times oxygen, which is also 0.015. And we need to be careful about units. So this is molarity, and this guy is molarity per second. So when I plug this in, 0.015 squared times 0.015, I get, I didn't get that last time. What did I do? Oh, I don't think I finished squaring it. All right, so I have 0.048 meters per second equals K times 3.375 times 10 to the negative 6. 3.375 times 10 to the negative 6. And we have molarity squared times molarity, which is molarity cubed. Okay. Now I divide both sides by that. And I get 14222. Okay. And my units are meters per second. And then I divided this side by meters cubed. So this meters canceled out with one of these. So I'm left with my rate constant K equal to 14. Let's see, I have 2 sig figs, so it should really be like 14,000. And my units are 1 over molarity squared per second. And I believe that is the end of our notes.